All right, it's time to start. So we ended up last time with fields, and I showed you some examples, and in particular, the last field that we looked at was the field of what was a finite field with 3 elements. So now there's 3 pages left. So let's discuss first this. What are the roots of this polynomial in F2? What does this mean? Well, if you want to answer this first question, we need to find x in F2 such that p of x is 0. But luckily, there's not that many elements in F2. So this means x is equal to 0 or x equal to 1. Those are the only elements in the field that we can even test for this polynomial. Well, if we now compute p of 0 is 0 squared minus 1. This is 0 minus 1. This is this is 1. Remember that that minus 1 mod 2 is 1 because we can see above. Well, this is F3, but in F2, 1 and minus 1 are the same. So 1 is the inverse, the additive inverse of itself. All right, what about 1? So if you compute p of 1, then we'll get 1 squared minus 1. And 1 times 1 is indeed 1, even in F2. So this is 0. So this means the root is 1 in F2. And if we now consider x in F3, then we could compute f of 0. Sorry, p of 0, p of 1, and p of 2. Well, p of 0, this is interesting, is 0 squared minus 1. But minus 1 is not 1 anymore. This is now 2. So notice that these are not the same. This is in F2 and this is in F3. So this might be confusing, but this is just what we have to get used to when we work with finite fields. Regardless, it's not 0. If we have p of 1, then this is 1 minus 1, which is still 0. But p of 2, and now we have to actually use this table, or just remember that 2 squared in F3 wasn't 4, but modulo 3, it is 1. And then if you have subtract minus 1, then we actually get 0, if I'm not mistaken. Yeah, that makes sense. So in this case, we actually have 2 roots. So this is somewhat something new to get used to, that the number of roots of a polynomial depends very much on the field you're in. So let me skip number 2, but do think about this. So think about whether you can find polynomials that have roots in the field or not, because as we've seen that q of x, which is x squared plus 1, doesn't have roots in R, but it does have roots in C. That's one example. And if you take, for example, R of x, I believe if you take R x to the 3 minus x squared plus or minus 1, let's try plus 1. Try to check what this is in F2 and F3. So there's interesting things happening in those fields. Okay, so a definition that we need now, because this discussion really leaves us with a question. when are we guaranteed that that a polynomial has all the roots in the field? And the answer is we call this algebraically closed. So algebraically closed fields are exactly the fields by definition, where polynomials have a root. If it's unconstant, it has a root in this field. So this means, in particular, the book says it somewhat differently, but it boils into the same thing. Because if you have one root and you factor out the root, so say p of x, such that p of x0 is equal to 0, then p of x can be written as x minus x0 times q of x. And this is degree of p minus 1. And then you have, again, fields, a non-constant polynomial in f, and then this has degree, this has, again, a root in f if it's algebraically closed. And then you can like go on and do and factor all these. So in the end, you do have n roots in the field for a degree n polynomial. And well, this discussion now would have been easier if you finished the discussion above, but could someone maybe guess at least some of these? So three of them, well, two of them should be clear maybe. Yes, C is closed, algebraically closed. R is not, definitely not, because we have this polynomial x squared plus 1, which doesn't have any roots. And if you look at x squared plus 2, there's actually is a polynomial in Q as well, like a polynomial with coefficients in the field Q. So for the same reason, Q and R are not closed. And actually F2 is not closed either. I think this polynomial that I mentioned above, so if you have x to the 3 minus x cubed plus 1, so if we consider this polynomial, then R, so in F2, then R of 0, well, x3 and x to the 2 is 0, so that's just the constant survives. And R of 1 is equal to 1 minus 1 plus 1, so this is also 1. So this has no roots in F2. Well, the theorem below is just making this, just proving this fact. Now the last thing that I want to say in this subsection as well, a field has been defined so that we can replace the real numbers with it. So think about the real numbers, and we've a little bit talked about the complex numbers as prototypes for some nice behaved sets with operations. And nicely behaved was it's just another word for they have axioms that they adhere to. So a vector space can be built over a field and not just R, because a field has all the nice properties that R has. And so as you'll see that these are exactly the same axioms as before, as we had in week number 1. Only difference is I had to go through the tech document and replace every R with an F. So you see that the scalars are now field elements. So they could be complex numbers, they could be real numbers. You can even have a vector space over F2. Say, for example, you have let's go to the examples. So you could have, for example, the vector space of 2 tuples made up of 0, 0, and 1s. So this will be just the set of 0, 0, 1, 0, 0, 1, and 1, 1, because each entry has to be an element in the field. And this is just the n tuples in the field. And so this will actually be a vector space over F2. And you would just write the vectors in the same way that you've always written vectors in this course. And scalars can be multiplied with the vectors the same way, only that now we have to be more careful what are scalars in our case. We have to be very specific which field we want. Well, now it's not a surprise that if we can form tuples, we also can form matrices. So we can just make n by n or n by m objects with entries in the field. So we could, for example, have a matrix 7 plus I 8, 0, I times 5, and minus 3. So this would be a matrix of size 2 by 2 with complex entries. Same with polynomials. So polynomials are not restricted to having real coefficients. We can have any field elements and the S coefficients. And we can also, this is the special property of complex vector spaces. Every complex, so the complex numbers can be thought of as a real vector space of dimension 2, because remember we had the basis 1 and I, and then Cn is a real vector space of dimension 2n, where you basically just, instead of having z and w, which looks like a plus ib and c plus id, you could you might as well, I mean, you have 4 real entries that make up 2 complex entries, so you might as well write them as a, b, c, d. And this really tilde symbol, this snake symbol, just means there's like there's isomorphism, but I'm not making this precise. Okay, so right, as a remark, this shows the previous discussion mainly. This the roots of a polynomial depend very much on the field that you're in, which field is allowed. So this is very important that you specify it's a vector space over the reals, the complex numbers, and so on. For example, the vectors I2 and minus I2i are dependent. Sorry, this should be seen. So if you want to find linear combination such that I2 alpha times I2 plus beta minus 1 2i is equal to the 0 vector, then there are no such solutions in R. So no solutions for alpha and beta in the real numbers. That just is not possible because I and minus 1 are literally 2 vectors pointing in opposite directions if you think about this as a real vector space. But alpha equals 1 and beta equals I is a non-trivial combination with complex coefficients. So these vectors are linearly independent if you think about C2 as a 4-dimensional real vector space, but they're dependent if you think about this as a 2-dimensional complex vector space. So again, the scalars, the field that connects the scalars makes all the difference. It's a very subtle point, but it's very important. And we haven't made the final yet, we haven't thought about this, but it's possible that these subtle differences will be the difference between true or false. So make sure you understand this, and if there are questions, please ask now. Okay, let me skip this discussion. There don't seem to be any questions. Let me skip this discussion and just point out that this is another example, another instance where the field matters. So it's a very interesting example, but the same point, it's the same takeaway. And then this is a remark. So in the book, where we have examples 5.2, 5.9, and 5 to 10. Everything that we did so far, we've seen matrices over different fields so far, but the determinant, eigenvalues, all these things still apply for other fields and vector spaces of these fields. So as an example, if we say that that C2 is a complex vector space, and I sometimes read CX for complex, then we can consider what do you want? 0, 0, 1, minus 1. Is a matrix in MAT2C. So we upgrade the field to C. And then this means in particular that T, so we can think of T sub A is a transformation from C2 to C2. Everything is the same as before. Like we've seen these things before. Now only the field is different. And eigenvalues. So V in C2, which has now complex entries, is an eigenvalue, or sorry, eigenvector. If A times V is equal to lambda V for some lambda in C. So this is also now eigenvectors are allowed for complex eigenvalues. So we still want that eigenvectors are non-zero. That hasn't changed. And now still true is that that eigenvalues are roots of CA lambda, which is the determinant of A minus lambda IN, and this would be lambda squared plus 1. So everything works as in real setting. So every definition, the determinant can still be computed. So the determinant has still the expansion in terms of cofactors. The only difference is now this polynomial has solutions. So the only difference, let me maybe write this as the last point, then I want to move on. So the only difference now CA lambda has eigenvalues because C is algebraically closed. So that's the whole idea. This page is a duplicate. Let me delete this. Okay, this is it. So in the future, starting today, we're going to be talking about vector space over fields, and I hope that I could somehow take away fear from you, because they're not any different. If anything, they're better because they don't have this problem of being non-algebraically closed. So yeah, whatever. Like if you do feel like this is field sketchy, then look at these examples, please. This will give you examples of how to work with the general vector spaces over any field. And looking at examples might show you that actually everything is the same as before. Algebraically closed means that that a non-constant, it's a definition here, that a non-constant polynomial with coefficients in f also has a root in f. This is just something that the book also defines this. Any other questions? Oh yeah, absolutely. That doesn't go away. So you have to still worry about geometric and algebraic multiplicity to agree. Because there are still, yeah, that's still an issue. Any other questions? Okay, then with 20 minutes delay, we can start now the new lecture. This is actually the content that was planned for week 10. So let's see how far we get through this. This is following section 6.1, and in the remainder of this the semester, we'll be looking at section 6.1 to 6.4. And it's actually, there's a nice theme to the end of the lectures here. So you can think of a diagonalizable matrix as being something that has a nice form, and we call this the normal form when it's diagonal. So as we've seen that if diagonalizable means that in some matrix, in some basis, the matrix has diagonal form, and that makes it easier to take powers, to multiply them, and many other things. So now some matrices, we've seen that diagonalizability is rare. It doesn't occur for all matrices. So the question that we're going to answer in the rest of the semester is, what are the canonical forms, the normal forms for all the other matrices? So say it's a non-diagonalizable, can we still have some normal form that we put it in to make it nicer? And in these sections 6.1 to 6.4, we're going to do this step by step to arrive at all matrices. But today we're going to start with triangular matrices, or triangulizable matrices. So this is very much the same spirit of diagonalizable matrices, only that we now define something else, that which is triangulizable, and we try to find a basis in which a matrix has triangular form or upper triangular form. Okay. So the first definition that we need here is upper triangular. So a matrix is called upper triangular if it doesn't have entries below the diagonal. And I think this makes sense because then you can see it's just this triangle in the upper triangle of the matrix is occupied with non-zero coefficients. So for example, this would be an upper triangular matrix in MAT224. And right, I forgot to say, for the rest of these nodes, I'm just going to assume that V is a finite dimensional vector space over a field F. And this is going to be true for the rest of these nodes, because I don't want every time to say, let this be a vector space of dimension n, which is finite over F, and so on. There's enough to set up all the discussions and theorems. Okay, so with this, the next thing I want to define is an invariant, or also called stable sometimes, subspace, which is, for a transformation from V to V, is subspace of V, which isn't, which is mapped into itself. So this means that if you think about this graphically, if you have V and T goes between V and V, then for some subspace W, this is mapped into W again. So it doesn't actually have to be, vectors don't have to be mapped to themselves. You can still stir around the subspace W in itself. But if there's a vector in W, then the image is also be in W. Some other vector maybe, but also in W. Canonical form and normal form are the same. So yeah, oh, I used both words. Okay, yeah, they're the same. It's the preferred way to represent a matrix if it has this form. All right, so let's look at examples for invariant subspaces. The first example is just the projection onto the xy plane. So I'm just going to draw a three-dimensional vector space over any field. Doesn't really matter which one it is. And then we have this xy plane sitting in here. And if you project every vector down, so you just forget the z component. So x, y, z goes onto x and y and 0. Then it is clear that if a vector to begin with has 0 z component, it will still have 0 z component in its image. And this means that every vector in the plane will remain in the plane. And so the plane will be mapped to the plane. And therefore, this is an invariant subspace in F3. Likewise, if you have the 0 subspace, because so T of 0 is 0 for any transformation, any linear transformation. So this means that that the subspace, which is just contains the 0, will also be mapped to itself. And of course, if you have the entire subspace, the entire space is subspace, then T of V by definition will be in V, and so this is also invariant. Another example that you could maybe think of is in F3 if you rotate. So if you rotate along this axis, so a vector here might be sent to the vector here in the plane. So it's just rotated. Then you have invariant subspaces, which are again the xy plane and also the z-axis. Because if you rotate anything in the plane, it will be in the plane, and everything in the z-axis is just unchanged. So just another example that I just thought of. Okay, so I'll give you now 3 minutes to discuss this discussion. Think about a linear transformation, which is in a certain basis given by this particular upper triangular matrix. And I wanted you to answer the 2 questions. Is span of V1 invariant? And can you find, moreover, 3 subspaces which are all invariant? And if you solve question 1, then it will hopefully give you an idea how to do question 2. Yes, the blank entries are zeros. So whenever there's something missing, then this is just 0. All right, any ideas? So first, number one, is the span of V1 invariant? How can you justify this? So V1, if we work in with matrices, then in beta, this vector has the form 1, 0, 0. Right, exactly. So Gensi just did this computation, but then without using coordinates, but this is actually, I guess, the idea behind this. So now if we multiply this matrix with 1, 0, 0, we see that we only get this entry. Every other column multiplies to 0 with this vector, and so this is 2 times 1, 0, 0. And so because matrix multiplication is set up, this matrix set up, so that this is exactly the tuple representing T of V1. This means that T of V1 is really just 2 times V1. And so this means it is still in the span of V1. And every vector in the span is some multiple of V1. So we could just, instead of V1, we could really multiply this with like some C in here. Okay, does that make sense? So basically, because nothing is in here, we will not have any contributions in the lower, so in the lower entries. So this means the vector a0, 0 multiplied with this will always be something at the top and then zeros. Okay, so any idea to the second question? Yes, that is true. So we could take 0, this span, and all of V. Let's try to not use 0 because 0 is too easy to guess. And actually, I didn't exclude this. I didn't think about that. This is actually also valid. But I'm looking specifically for something else. So maybe can you find some other span of vectors that will also be invariant? Well, we don't really know if there are eigenvectors here, and I didn't provide information whether there is it has eigenvectors, it is diagonalizable, and any such things. Yes, so Jordan just wrote in the chat that we can kind of imitate this first step and say, well, W2 is the span of V1 and V2. Now, what is a vector in this span? So say V is in the span. And this means in the basis, beta, V looks like X, Y, and 0, right? So we can have any X times V1 plus Y times V2. So now what happens if we multiply this upper triangular matrix with a vector that has only so many non-zero entries on the top? So now observe that 2, 1, minus 1, 0, 3, 1, 0, 0, 3 times x, y, 0 will be 2x plus y, 3y, and 0. So the matrix multiplication is exactly made in such a way that that these non-zero entries will only interact with these two columns. So the zero entry will just ignore the whole rest. And if there are zeros below a certain point, exactly the same column, then this zero on the bottom is always going to be zero. So maybe just stare at this multiplication for a bit, and then it makes sense. No, and Andrew's asking about something that it's going to be on the next page. So this example, this discussion, is supposed to lead us to a general fact about upper triangular matrices. So let me just finish this. So this is now again in the span of V1 and V2, because this means exactly being in the span of V1 and V2 in this basis means we have something non-zero, anything really here, maybe zero actually is allowed, and zero below. And then, as you can guess, so this means that W1, which is the span of just V1, W2, which is the span of V1 and V2, and finally W3, which is the span of all three. But this is just V. They're all invariant. And moreover, W1 is contained in W2, is contained in W3. And this contains, of course, the trivial subspace. All right. So this is the idea. If we just keep adding one vector at a time to the span, then we always get subspaces which are invariant, exactly because of the shape of the matrix, because of this upper triangular form. And as Andrew was asking, the next proposition exactly captures this. So linear transformation is upper triangular in a certain basis, if and only if for each I, these successive spans of the first I vectors are invariant. Let me maybe just not spend too much time on this in the proof, but let me give you an idea. And the book is then, I think actually the book doesn't have a proof at all. 614. Well, they argue this with something beforehand. Yes, so a sketch of the proof is just the following. So in one direction, so let's suppose A is upper triangular. So this means there's something on the diagonal, something here, and there's zero on the bottom. Then a vector, so V, is in the span of the first V1 to VI, is equivalent with V has something on the first I entries and then zero below. And now this is just a generalization of what we observed in this discussion. And this is nice. This is the idea that if you do something 3 by 3 and you understand it, in that case, you can just generalize it to any length. So this means now that A times V, and I'm gonna skip all the coordinate tuple and real vector distinction. This would be a matrix product of something that is upper diagonal with a vector like this, and you can see that exactly at this ith column, this is the last column, which has a non-zero entry left of the ith row, oh, no, sorry, the ith row is the last row where there's anything non-zero in this spot or left of it. So everything here in this box is 0. And everything, so this means the result will have no non-zero entries below this thing. So you can convince yourself that the pairing this vector, this column vector, with any of these rows will give only non-zero entries if we above this ith row. So this means this is again something of the form okay, this is half of the proof. Let me also sketch the other half. So the other direction goes as follows. Now we suppose beta is the basis as above, and wi is equal to the span of v1 to vi, and this is invariant. Now, if we apply t to vi, and then I look at this in the ith basis, so in the b beta basis, this will be the ith column of this matrix. Remember, this was the algorithm to find the matrix representing a transformation. But by assumption, because in particular vi is in the span of v1 to vi, we know that the resulting vector has to be also in the span. This is because of buff invariance. So this means what we can have is only a linear combination of the first I vectors. This we know because wi is invariant. But then what is a linear combination of the first I vectors where everything else is 0 in the basis beta? Well, this is exactly a tuple a1 to ai and then zeros. So if this is the ith column, and we can do this for every column, then this implies that the matrix has the form that there's that the ith column has entries a1 up to ai and then zeros. But this means that the first column, for example, has a entry in the first non-zero entry in the first entry, and then zeros, and so on. So this means that it actually is upper triangular. Any questions about, actually the second part was almost a proof. Any questions about this argument? So now, in accordance with diagonalizable matrices, if we call them diagonalizable if there is if the basis that makes them diagonal, the transformation. We call the transformation triangulizable if there's a basis such that this matrix has upper triangular form. So this definition is really like the spirit is very similar. And now the question is the same with diagonalizability. In which cases does such a basis exist? So does it exist for all matrices, or what conditions do we have? For diagonalizability, we use eigenvalues. In this case, it's actually simpler. So a linear transformation is triangulizable if and only if the characteristic polynomial has as many roots as the dimension of the vector space. So it has dimension of v roots. And I'll not prove this. I'll just refer to the proof in the book. All right, so let's try to answer with this theorem this following question. If you have a matrix with complex entries of size n by n, is there always an upper triangular matrix B which is similar to A? So count it with multiplicity means say it has roots 1, 2, and then 2 again. So for example, x minus 2, x minus 3 squared has 2 roots, but with multiplicity it has 3 roots. Yes. So whenever we don't specify whether we mean the algebraic or the geometric multiplicity, it always means the algebraic multiplicity. Because in particular here, when we talk about the characteristic polynomial and the roots, then only the algebraic multiplicity makes sense. Okay, any ideas about this discussion? Yeah, we need to use that C is algebraically closed. And how do we proceed? Adrian.
Yeah, can we just say, so because C is algebraically closed, we know that like such a basis exists, and therefore we just have to find the corresponding change of basis matrix, and that's basically the definition of similarity.
Yes, exactly. So let me just maybe put in two words there, because first of all, A. So when we talk about so TA as a map from C to the N to C to the N depends on the basis. So like this transformation depends on which basis we in the standard basis. So we can just say in standard basis E1 to En. Right, and then now, as Adrian said, this is so the characteristic polynomial of C A of lambda is a polynomial in of degree n with complex coefficients, and it has n roots by the fundamental theorem of algebra. And now, because it has in roots, so by theorem 618, this means that A is diagonalizable. And this is just by definition, there is some basis such that the transformation in this basis is upper triangular. So that we could just call this B. And a change of basis matrix Q such that, well, A is the matrix representing the transformation in the standard basis. So this was, let me call this alpha. And now we know that B is that we found this new basis beta, in which it is a different matrix. And now we know that if we have a change of basis matrix going from one basis to another basis, and in particular, for any two bases of a space, you can always compute this the change of basis matrix. This will be okay. Now I forgot to move this. There's some Q and Q inverse such that we can change the basis. And this means A and B will be similar exactly by this change of basis transformation. Any questions? Okay, before we take the break, let's see, it's page 3. Okay, so there's one more page in section 6.1. Would it? Oh, yes. It's so similar that I actually got confused myself. Thanks, Yuan. No, sorry, who was it? Aditya, thank you. So this should be. So it's a very same same idea, very same spirit as in diagonalizability. Okay, so before we take the break, let me just maybe introduce this notation discussion, and then we can review this discussion after the break. So this notation is kind of an abusive notation, because if you have a polynomial, we usually just think of this as a function from f to f, so from field to a field, say R to R. So this is p of x, and we just do this by we just take you just exponentiate the number, the argument, then we multiply them with the coefficient, and then we sum them all together. But all these operations really make sense for matrices as well. So we could also think of this as a polynomial, as a function from matrices to matrices. And when we say P of A, we just really take the exponential of the matrix. And so A to the K is really just A times A times A K times. And then multiplication with a scalar in the field also makes sense. And so we just define this to be the polynomial applied to the matrix. And now the discussion that I want you to think about, maybe not during, but right after the break, if you have two matrices which are similar, then you can show that the value of any polynomial on this matrix is actually going to be similar to to each other as well. So if A and B are similar, then the value of P at A and the value of P at B will be matrices again, and they will also be similar. So how can you show this? It's more or less a quite brute force computation. And then suppose that that A is upper triangular. First of all, compute the characteristic polynomial, and you have to do like some expansion, some cofactor expansion. And then apply this characteristic polynomial to A itself, the one that you found in the previous step. Okay, let's take a 5-minute break, and we'll resume at 2:12, and then we'll actually come back anytime you want to think about the discussion, and at 1:15 we'll resolve this discussion. Any questions before? Like, is this a statement of the discussion clear? All right, then let's take a break and think about this when you come back. All right, I resumed the recording. I just saw there's a question by Benjamin. So to answer this, first of all, diagonalizable matrices are all upper triangulizable, or like all triangulizable. Because if you diagonalize it, it has a particular upper triangular form. So that's a subset of all triangulizable matrices. You could draw this like this. This is all the. So if you think of the set of all triangulizable matrices, then the diagonalizable matrices are specific ones inside there. To show that they're not the same, you could show maybe as an aside. So 1, 1, 1 is upper triangular. But not diagonalizable. Yeah, you can think about that. Okay, so let's discuss this this for the first point. What about P of what is P of A? Any ideas? So we can just plug in that this is P of QB Q inverse, because QB Q inverse is not a matrix. And so if we have P given as the I'm talking about the first the first discussion point. So if this is AN Q B Q inverse to the N, and so on, and then we have A0 in. Then for each of these factors, we can well just multiply them out. So if we have QB, Q inverse, QB, Q inverse, QB, Q inverse, and we have this n times. But we see that the Q inverse and the Q's in the middle, they all cancel. And again, as before, we can just have Q, we can just replace IN with Q, IN, Q inverse. And now we see that this is really AN. Should be aware of the space here. Q B to the N, Q inverse, A0, Q, IN, Q inverse. And then we can, as a last step, write Q AN, BN, A0, IN, Q inverse, and this is just Q and Q inverse multiplied on both sides to PFA. Sorry, PFB. So this is what I meant by it's just a straightforward computation. So you can just plug in what you want to start with, and then you just go until you have what you want. Okay, so for the second one, let me use a new page. Right. So what is the determinant? What is the characters polynomial? CA of lambda. So I think this is what Jensi was referring to. So if we have this matrix here, and we want to compute the characters polynomial of this, well, this is equal to the determinant A minus lambda IN. But now we see that this is really the determinant of lambda 1 minus lambda, lambda 2 minus lambda, all the way to lambda n minus lambda. And we don't really know what's here, but it doesn't matter. These will not matter in the computation. So how do we compute this? Jensi, how did you compute this determinant? Expand, yes, so we can expand along the last row. So the only non-zero entry here is the last one. So this is lots of zeros. And then we have -1 to the n plus n, this is the cofactor with the right sign, lambda n minus lambda times the determinant. Determinant of what? So this is the beauty. Well, if you strike out this and this, we get the minor that we need. And so the determinant here will be lambda 1 minus lambda all the way down to lambda n minus 1 minus lambda on the lower right hand side. And then again, we have some stuff here which we don't really need. And so we just keep going. We just keep going until we have only a number left. And then we see that this is lambda n minus lambda, lambda n minus 1 minus lambda times lambda 1 minus lambda. Okay, that was the first part of the second question. Now, what happens if we plug in A itself? So CA of A itself. So we apply the character polynomial of the matrix A to A itself. So so now the only tricky thing here, I guess, is what do we do? So lambda will now be replaced with a, but how does it make sense to subtract it from lambda n? Well, as you've seen here above, when we apply a polynomial to a matrix, the constant terms will have to be multiplied with in so that we can promote it to that we can promote this to a matrix. All right, so when we do this, we have actually I wanted to like, sort them in different ways. So we might as well right. So we have in times lambda n minus a. We have in times lambda n minus 1 minus a, and so on. And then finally have I times lambda 1 minus a. So now what will each of these factors be? Well, we'll see that each of these factors will look like lambda 1 to lambda n minus 1, and then we have a 0 on this and something here. And likewise here, we're gonna have lambda, actually, this is where I think I made a mistake before. So this is gonna be lambda n minus lambda 1, lambda n minus lambda n minus 1, lambda n minus 1 minus lambda 1. And then we have a 0 at the n minus 1, n minus first spot on the diagonal, and then in lambda n minus 1 minus lambda n, and something here. And now I guess there's this argument to be made, which I'm not going to be very precise about. But if you multiply these two, if you multiply all these matrices that follow as well, then the first two will be upper triangular, except the lower two will be 0. So you can see if you multiply the last, column here, and this is really, this is the last column in this matrix, then the lower right entry will be 0. And same when you multiply, there's another 0 here. When you multiply the second last column of this matrix with the second last row in this matrix, then this will be 0. And so you get like 2 zeros now on the diagonal. And then if you keep going with all the other matrices in total, yes, sorry, I think I made a mistake preparing this. I thought that was a lazy argument. But let me just not continue this and just tell you that this is an exercise to this computation. I'm not sure if this is the right, I think this is the right way, but there's like some thoughts that have to be considered to show that this is actually 0. Yeah, because of the time, let me just go to the next, the final theorem of this section, and say that that this will actually be zero. So we want to show this is supposed to be zero. It's supposed to be the zero matrix. So this means that the characteristic polynomial of a matrix applied to itself will be zero. And this is true by theorem 6.1.12, which is called the Cayley-Hamilton theorem. This is true for any linear transformation that has as many roots as the space has dimensions. So if there's a polynomial with dim v roots, then this is true. And this is exactly the condition that it is triangulizable. And also for the proof of this theorem, I will refer you to the book. Any questions before we go to the next subsection about nilpotent matrices? I'll upload all the annotated versions later. I didn't. Oh, I think 9.1, there was a problem with my iPad. It didn't download the file. It was kind of corrupted. I'll fix that later too. Okay, so now that we've talked about triangulizable matrices, which means that they can be brought to upper triangular form, this is the next step in the general agenda to find normal forms for all matrices. And this is another kind of transformation that we want to bring in normal form. So this is not the final step yet. And for this, we define what it means to be nilpotent. So a linear transformation is called nilpotent if some power will be zero. I guess I didn't include an example here. But example is the matrix 0, 1, 0, 0, which is not the zero matrix. But if you square this, it will be zero. And of course, you can have examples in higher dimensions too. And then the least n such that this is zero, the power n to the n, is called the index of this nilpotent transformation. So in this case, the index, this is nilpotent of index 2. So with this definition alone, we can discuss the following points. So suppose that that n is a nilpotent transformation. Does it always have an eigenvector? If it has an eigenvector lambda, what can lambda possibly be? And lastly, suppose that that it only has one distinct eigenvalue, which is 0 of multiplicity dimension of v. Is T nilpotent? I'll give you 2 or 3 minutes to think about this. If you have questions, then just feel free to type in the chat or raise your hand. So Zach just commented on something in the chat, and yeah, I mean, it's good that you commented this, because this is a thought that maybe some of you have. But what does that mean? Like, maybe can someone respond? Like, is the point that Zach raised really a contradiction to having an eigenvalue? Or maybe is that even maybe you should turn this this problem into an opportunity and see it as a solution instead of an issue, because that is actually the way that you can answer this discussion, this first question. Yeah, Andrew. Andrew's comment is good. So Andrew, can you explain how you got there?
I guess like how I started thinking about it is that since it's nilpotent, it must have a non-trivial null space, and if it has a non-trivial null space, then it must have an eigenvalue of 0, because some dimension is getting squished into the null space.
Yeah.
Transformation, and
yes.
the vector would just be like some vector in the null space.
Right. So that's correct. It's just somewhat different than what I was expecting. So let me just write this down and then try to bend it to where I want it to be. So M nilpotent has to mean that the kernel of N is non-trivial. Well, why is this? Now we kind of have to argue why this is. So if n to the n is equal to 0, then for all v non-zero, n to the n of v is equal to 0. And so this means that n applied to n to the n minus 1 of v is 0. And so finally, n to the n minus 1 of v is equal in the kernel of n. Now, the only thing that I just realized that we have to be careful about, so this has to be non-zero. For some v, because otherwise the index was n minus 1 and not n. So if it was 0 for all v, then the index couldn't be n, because only the 0 vector has kernel to the equal to the entire I think it makes sense. So if right, only the 0 vector sends everything to 0. If it's not the 0 vector, then there has to be some vector sent to something non-zero. But yes, so as Andrew was arguing, because there's something non-trivial in the kernel, this means that this element n to the n minus 1 v is an eigenvector to lambda equals 0. I didn't even have space here. This is kind of unfortunate. So let me refer to 2 and 3 are below. So suppose that suppose there is some eigenvalue. Can it be anything else but 0? Yeah, I think Adrian, that's what you wrote in the chat. So if you suppose n times v is equal to lambda v for some v non-zero, then if you keep applying n, so then n applied to nv, which is just n squared of v, will be n applied to lambda times v, but because it's a linear transformation, we can bring the lambda out. So we have lambda n of v, this is lambda squared v, and so on. So if you do this n times, then 0 has to be n to the n of v, because this is the index of this nilpotent map. And by the above, this is just lambda to the n times v, but v was non-zero. So lambda to the n has to be 0, and so lambda has to be 0. So this means the only eigenvalue of a nilpotent map is 0, and it always has an eigenvalue 0, which is which is already very interesting that we can get so many things out of a very plain definition that just says some power vanishes. Any questions? So the last point, number 3, is somewhat tricky. This is almost like a lemma. Something that the book mentions in the text as an aside. Doesn't really, the book doesn't really capture this doesn't make this into a big thing, but I think it's interesting to mention it. So if what was it? So if n has eigenvalue lambda equals 0, what was exactly the I want to call this t. So we don't even know that it's nilpotent. So just any transformation t has eigenvalue lambda equals 0 with multiplicity m lambda, which is the dimension of v. Then this means that the quadratic polynomial of t is equal to lambda to the n. And now we apply Cayley-Hamilton, this theorem that we just ended up with the last hour. And we know that 0 has to be equal to ct of t, and this is t to the n. So this means that it is in fact nilpotent. Okay, so time is running as always. Any questions about nilpotent? About nilpotent transformations? To make one more definition, and then we can go to an example with a very explicit transformation that is nilpotent. So before that, I want to first mention that if you have a nilpotent transformation of a certain index, and you have a vector that is non-zero, then it might happen that some power of n that is less than the index will actually send this to 0. So this depends on the vector v. Depends on v. But what we do know is k has to be between 1 and n. So it can be greater than n, because then n to the n just like sets everything to 0. And it also can't be anything less than 1. This is not factorial. Okay, so one more definition before we can get to an example. If we start with a non-zero vector and we keep applying n, then all these elements that we get, like a chain of elements, we just keep applying n over and over. It's called a cycle generated by V. That's what I wrote here. So you start with something non-zero, and then you apply n one times, you get nv, and then you get n squared v, and so on. And then eventually you have n to the k minus 1v, and then n to the k v will be 0. So we don't include this into the cycle. And we call v the initial vector of the cycle because it's the rightmost. So we kind of think of this as a chain of elements that get sent to each other by n, and we start from the rightmost. Of course, if we have a family of vectors, we can just span a space with them, and so we call this the span of the cycle, the cyclic subspace generated by V. And the k, the length of the cycle is denoted by k, and this is actually called the length of the cycle. Okay, this is a lot of just conventional notation and names. So to let this sink in, I'll give you an example right now, and then or I think it's discussion, and then we can apply this and see how this works in detail. So the first question is the transformation that takes the second derivative of a polynomial. Is it actually this is supposed to be 7? Sorry. Is this transformation nilpotent? And if so, what is the index? And then also, can you find a polynomial in P7 of f that generates a cycle of length 3? I'll give you 2 or 3 minutes. If you have questions, please just ask or write in the chat. Any ideas? I suspect that the notation, the new words, is more complicated than the the actual math behind this, because that's something we've been talking about since week 3 or 4, maybe 2. So first of all, is this operator, this transformation, is this nilpotent? Yes, you're right. It is nilpotent. So let me answer this here. Yes. And exactly. So the index of d by dx squared on P7 R is 4, because if we apply this 4 times, then we have d by dx squared to the 4 is equal to d8 by dx8. And if you apply this to p of x, something of degree at most 7, this will be 0. But everything below that, so if you like took the power 3, then we'd have the 6th derivative, and then there could be non-zero. So for example, x to the 7 would be 7 factorial times x. No, it's just 7 factorial. And no, times x. And it would not be 0. So this is in fact the index. And then can you find a polynomial that generates a cycle? I guess I already gave it away. I give one instance. Please take a simple one. It should be quick to write. Yeah, x to the 6 works. Right, because otherwise, yeah, exactly. Otherwise it would be too long, I guess. So the second point is p of x is equal to x to the 6. And then we see that d squared by dx squared of x to the 6 is equal to 6 times 5 times x to the 4. So this is 30 times x to the 4. If you apply this again, we have the d4 by dx4 x to the 6. This is equal to 6 times 5 times 4 times 3 times x squared. So this is equal to 30 times 20, 360 times x squared. And no, I believe this is still too long. Yeah, exactly, Adrian, you're right. So this is too long. We need to cap this one more. So we just need to take x to the 5, because the cycle would contain the first one, the x to the 5, the first derivative, the second and the fourth derivative, and the 6th derivative. And for x to the 6, we have 4 elements which are non-zero. That would be cycle of length 4. But the question is asking for a cycle of length 3. So if we do this again now, 5 times 4 times x to the 3, this is 20 x to the 3. Here we have now 5 times 4 times 3 times 2 x. This is 120x. And the next one will be 0. So d by dx to the 6th power of x to the 5 will be 0. Now I got to shrink this all down a little bit. So this means that the cycle alpha is x to the 5, 20x to the 3, 120x, and that's it. So this is a cycle of length 3. If you want another example, I don't want to look into this too deeply now, but 6.6.2 in the book just gives you the matrix 0 to 1 minus 1 0 0 1 0. There's a 1 and the rest is 0. So you can verify that a to the 4 is 0 while a to the 3 is non-zero. So it's a transformation from R4 to R4. This will be an nilpotent transformation, and you can, and the book actually gives you an example of a cycle. No, the cycle does not contain 0. No, so also Shun's question is wrong, because we start with the initial vector. Did I not think the definition? Yes. So if you look at this definition 621, then we start with the original vector. In this case, it's x to the 5, and then we include every element that we get by applying n once more, and then the last time 0, which will eventually occur because at the latest at the nth power will all be 0. But maybe before that, that's where we cut, but before the 0, because yeah, if we span the space, this is like kind of a hint. If you span a space with this family of vectors, we don't really want a 0 there, and it doesn't really, zeros are usually not very welcome, except for subspaces that we need them. So, okay, any questions about this example? Does that does that explain the notation of cycles and lengths and so on? Oh, by the way, the cyclic subspace generated by this, so CF x5 would be exactly all the odd powered polynomials, except not 1 without the constants. Yeah, so this is maybe not so smart to say. X to the 4 would have worked as well, I believe. You would have gotten x to the 2 and then a constant. So yeah, that would have worked as well. You could have had as an alternative cycle, you could have gotten x to the 4 12 x to the 2 and then just 24. Okay, so let's look at this proposition, and maybe, yeah, I want to get to the notation of cycle tableau before we end, because that's something you might have to see twice, at the end of this and the beginning of next week. So the proposition, which we're not going to prove, I suppose, says the following, and this is actually already part of the discussion. So this is see the discussion above. It says that if you have a cycle of length k, then the last element that is sent to 0 will necessarily be an eigenvector with eigenvalue 0. So that's nothing new. Another thing that this proposition is claiming is that the subspace generated by a cycle will always be invariant for n. You can think about this as an exercise. And then this cycle alpha, this is the most interesting part, number 3. The cycle alpha generated by a vector is independent, and hence it's a basis for the cyclic subspace. This one, so number 3, this can be disapproved by induction. But I think we'll not really look at this just because of time constraints. It's very similar to a previous proof induction that we've done in this class. So it shouldn't be hard for you to look in the book, read this. It's not very long either, and then understand it. If you have questions, so you're of course welcome to ask me about the proof. Okay, but like the most shocking result of this proposition is the last one, definitely, that when you have a cycle, you can generate an invariant subspace and you immediately get a basis for it. Okay, so I plan to go about 5 minutes over time because I want to introduce you to a notation that's going to be very important for this section. So when we have a cycle, as just seen in the example, and it has length k, then what we do is we just write k boxes for this. So let's say these are k boxes. And we represent, and in each of these boxes should represent one vector in the cycle. So we just think about the first box being the initial vector v. The second one, of course, is then n applied to v and so on. And the last one is n to the k minus 1 applied to v. Just because the elements itself don't really matter as much as the structure of the cycle. So we want to have an easy notation because, to be honest, all these indices kind of are cumbersome to write. We just want to have an easy notation to memorize how long is the cycle. And in the next step, we see like how many cycles we have, because this was step 1. We associate a row of boxes to a cycle. The next step is we associate to different cycles. Each has a row of boxes, and we just sort them by length and put them on top of each other. So if we have cycles alpha 1 to alpha r of length k1 to kr, then we just think about them as boxes that we can stack. So let me try to draw an interesting example. The box are getting not box anymore. So I don't know, maybe this is, yeah, so this might be this is a cycle alpha 1, alpha 2, and 2, 3, 4 up to alpha 5. So we have 5 cycles here. This is what this this cycle tableau, which is this what the name of this is representing. And it tells us, well, this is the vector v1 sits in here. This represents the vector v2 and so on. This is the vector v5. This will be the vector, I mean, the first, yeah, let me first put in the k's. So k1 is 4 because the first cycle has 4 boxes. K2 is 3, K3 is 1, K4 is 1 as well. And K5, sorry, no, they're both 2. And K5 is also 1. Okay, so this means this is n to the 1, 2, 3 applied to v. Yeah, I think that's all the information that this tableau is encoding. So since we stop at this point, we're gonna stop like soon. It might be confusing, and you might be asking, why do we need this notation? But the proposition 6.2.4, which is about to appear, will need this notation in order to make assertions. And in the future of this section, we are going to want to refer to this notation and think about this as when we talk about different cycles at the same time. Any questions about this notation? For example, we could have represented from above. We could have represented the cycles x5, what was it, 120, no, it was 20x3, 120x, alpha 1, and alpha 2, which could have been the cycle x to the 4, 12x squared, and 24. These would correspond to the tableau, which is just 3x2 boxes. So this is not really interesting, but just to give you a feel for how we go from cycles to just this notation where we abstract away. Okay, so the discussion here, I don't think we're going to do this today, but let me just put in the right. I think it doesn't really matter which. Yeah, so I just wanted to put in a random tableau. And then the question is, which of these elements are necessarily in these subspaces listed below? So this is what we're going to start with next week. But for now, I want to end at this cycle tableau notation. Any questions? Okay, then let me stop the recording.